Good morning. I'm Larry Olson, President, Chief Engineer of Olson Engineering and Olson Instruments, located in Wheat Ridge, Colorado. This is our second webinar. The first one was on seismic geophysics for determination of the shear wave velocity in the top 100 feet at soil sites for International Building Code that was given in April by Dr. Ryan North, our principal geophysicist, and our project geophysicist, Travis Nielsen. So it's my pleasure to welcome you here today. Looking forward to it. There will be a recording put up on the web on YouTube, and everybody that's registered will get a link to that recording if you want to go back and look at the presentation again. So we're going to run this for approximately 1 hour. Any questions you have will be through chat. We're going to try to do 1 to 2 webinars a month as a company going forward, and appreciate the excellent participation and the many of you that have joined us today. So with that, I'm going to get right into a fast-paced presentation that will cover non-destructive evaluation of bridges using NDE methods. So the outline of today's presentation will start with non-destructive evaluation methods for bridge superstructure, looking at applications of pre-stress and post-tension girders, of course, reinforced concrete beams and columns, and a bit on corrosion evaluation on steel girders and anchor bolts for integrity. In terms of bridge decks, we'll be talking about the applications of NDE to bare concrete decks or thin epoxy coated decks that are still basically concrete. We'll also be talking about asphalt overlaid concrete, a more challenging problem to assess the condition of the deck, and white topping, that is concrete put on as a repair and bonded to concrete deck underneath. So I'm a member of the 228 Non-Destructive Testing Committee, as well as the ACI 342 Bridge Evaluation Committees, and I welcome my fellow committee members who may be listening to this presentation, of course. The committee has a very good report on non-destructive test methods for evaluation of concrete and structures. It's listed there. Many of the methods we'll talk about today are stress wave methods, but we'll also talk about some of the electrical corrosion evaluation methods, and also, of course, ground penetrating radar. But this is an excellent resource. It's part of the Manual of Concrete Practice that will give you more background and depth on the methods if you want to look at it. So in terms of the methods, NDE methods and applications, of course, we all start with visual assessment, the ultimate non-destructive testing method in some ways. We do NBIS inspections on very detailed assessments because we often combine our visual with non-destructive evaluation methods. In terms of concrete testing methods, we'll talk a lot today about impact echo, looking at cracking, corrosion delamination damage, a big one for decks, of course, honeycomb, void issues, thickness, and voided versus grouted post-tensioning ducts can all be identified and mapped out with impact echo. Spectral analysis surface waves, looking for cracking, getting depths of perpendicular cracks to the surface, void honeycomb evaluations, slower velocities associated with that, and getting direct measurements of velocity modulus. These first 2 tests are done from one side. Ultrasonic pulse velocity or tomography takes access typically to see much internally to at least a semi-direct angled or direct test from side to side, although you can test near the surface and get a basic measurement of velocity as well. A slab impulse response is a test used for integrity of concrete and looking for void below slabs on grade, concrete slabs on grade, such as an approach slab. Ground penetrating radar is probably the best known of the non-destructive evaluation methods, commonly used to map out steel, embedded, other metal, post-tensioning duct locations. Infrared thermography is a test we do use in support of it. It only sees a few inches into the concrete to find delamination. So we're not discussing that today for a lack of time to cover everything, but it certainly is out there as well. Ultrasonic pulse echo, common test or ultrasonic thickness testing to look at section loss due to corrosion in steel members, find cracks, and we'll talk about it in terms of anchor bolt integrity and length in concrete. The first case history talks about NDE, non-destructive evaluation methods for quality assurance of epoxy injection crack repairs. This project is a girder on the east side of Denver, bridge girder over the interstate that a truck carrying a very large forklift forgot that they were told, don't ever drive under any bridge in the United States. They forgot that. And so when they got to Denver, they plowed the girder. It did not fail it. It spalled and cracked it severely, but the pre-stress in this I-beam was still intact. So our company, along with Martin & Martin, John Lund, locally wrote an article about this project because they allowed the structural design of the repairs by Martin & Martin combined with quality assurance and left the girder in place, and it was repaired with quality assurance of those repairs. So this shows a picture of the epoxy injection. You can see also the mortar patching repairs that were done. To fill the cracks, a very good local contractor did the repair. We used three primary methods to check the quality of the repairs. Impact echo from the web wall there that was so severely cracked. The ultrasonic pulse velocity direct testing front to back and at an angle. And surface waves across the ingested cracks as well. On the right, there's two receivers. You impact it at one end, and that's about a 6-inch spacing between those two receivers. Looking at this 6-inch thick web, all these methods are mentioned in another group I'm active with, the International Concrete Repair Institute. I'm on the evaluation committee, and they have a guide for verifying field performance of epoxy injection concrete cracks is referenced in the lower left. So impact echo, many of you are probably familiar with it. You impact the surface and you look for a resonant echo from either the full thickness as shown on the left or a crack, a planar void, a reflector that's a change in stiffness and density. So you can see the echoes in the time domain, but they're not clear because it's very high frequency response. By doing, though, a fast-Fourier transform, you get the resonant echo peak, which is shown in the right. And the depth of that peak is equal to a shape factor. It does depend on whether it's a slab or a wall flat shape or beams and columns with circular to rectangular to square shapes. There are lower factors to account for the reduction in compression wave velocity. So basically, it's this factor of 0.96 times the velocity divided by twice the frequency of resonance or echo peak that predicts the depth. So a rough, close to normal velocity for concrete is 12,000 feet per second when factored. And if you take 12,000 feet per second divided by a resonant echo of 6,000 hertz, that says it's a 1-foot echo. 12,000 divided by 2 times 6,000. So this shows the results. On the right is a result. All of this was damaged, but this area was successfully injected in these 9 locations on this 6-inch grid. You see a single dominant peak that corresponds to a 6.3-inch thickness echo at about 12,000 hertz. On the left, though, is in the center, position 5. That result had multiple echo peaks, and the backside echo was shifted down in frequency, which indicates that the area was not fully injected. You're getting some other echoes in this result. So this was indicating this one area out of many tests were done, but out of these 9 test areas that are shown had a problem. So we then did ultrasonic pulse velocity. The nominally 50 kilohertz transducers are shown there. They're grease coupled typically with a light lithium grease. You can use an ultrasonic industrial or medical gel if you're worried about staining the concrete, which you should be. People don't usually like really black grease on their concrete. The lithium is relatively white. But you push on each side and you send. One is a sender, a source, and the other one is a receiver. They're matched frequencies. So as it shows in the lower right, you can test directly through, semi-directly at an angle, depending on access, or on the surface, but then you only see 1 or 2 inches deep. You're most sensitive to the surface. So the pulse velocity is equal to simply the distance divided by the travel time. So a test has been around a long time. Leslie and Cheeseman, back in 1949, came up with this general guideline that is still used for general concrete condition, ranging from very poor at slow velocities of less than 7,000 feet per second to excellent above 15,000 feet per second. And most concrete is in the range of 12 to 15,000 feet per second, being good to very good. So this is a general qualitative guide to interpret it. It obviously varies a lot, as discussed in the ACI guide, depending on hard or soft aggregates, the water-cement ratio, the mixed design strength. The faster it is in general, the stronger the concrete. So these tests were done directly through and at semi-direct angles, again showing some in the dashed lines, particularly slower velocities, less than 10,000 feet per second. So this was again correlating with the impact echo result and showing some isolated problems in that area. The final test we did is spectral analysis surface waves. This was first developed by my professor that I studied under at the University of Texas at Austin, Ken Stokey. And basically, he had started with it as the forerunner of multi-channel analysis surface waves, but to look at the soil and rock and velocities without having to do downhole or crosshole seismic testing. Sohail Nazarian, one of his first students that really ran with it also, has used it a lot on pavements as well. We've applied it to structures, to pavements, and to soil and rock sites. So what you see there is an impact source and two receivers basically hitting in line, running it into our Freedom Data PC. Measures the speed of the surface wave, which is about 56% of the compressional wave or ultrasonic pulse velocity for concrete with a Poisson's ratio of 0.2. So short wavelengths sample shallow, longer wavelengths sample deeper. And the velocity basically is equal to frequency times the wavelength. This allows the measurement of the depth, the velocity profile into a structure, and that can be related to strength in the condition of the concrete versus depth and depths of perpendicular cracks, as we'll discuss. So this shows example results from a filled crack. The coherence is a signal to noise ratio. It's generally near 1 over this frequency range of 0 to 50,000 hertz. But in the lower part is the so-called velocity versus wavelength. Velocity on the left, it's showing surface wave velocities from wavelengths of only about 15 hundredths of a foot up to the half-foot thickness of the web from between 7,000 and 8,000 feet per second, which is a very good velocity and normal for repaired concrete with well-injected epoxy-injected cracks. This is a result which showed an unfilled crack. Here, the surface wave velocity is much slower. Starting off at 1/10 of a foot, we got fairly high frequency, and going up to, again, the half-foot thickness, going from 2,500 to 5,000 feet per second. You can see the coherence is also affected. This is the cracks that we're testing across with the transducers spanning the crack area are just showing a slower velocity because it's not fully injected. I want to hasten to add the contractor actually had very few areas that were not well injected. It was a critical project. They went back and re-injected those areas, but they did an excellent job. And we're very careful with both all of the repairs they did and the epoxy injection. So this shows how you can do quality assurance. We make instruments ranging from the fairly simple to more complex. This is an impact echo gauge. It's our CTG2 is what it's called, but it basically goes into your Windows tablet or notebook, and it has a built-in solenoid impactor. It's battery powered on the handheld unit on the right. So that solenoid will hit the concrete when you pull the trigger. And there's a displacement transducer that you push on to couple it to the concrete. And you can see the echo result on the screen on the left predicting 5.2 inches. So this shows you the data in the field. It takes advantage of the audio port and capabilities of the Windows tablet or notebook to take the data. So that makes it a pretty economical gauge. This is an example of the data. You can see the time domain signal on the left, that's raw, unfiltered. On the bottom left is the filtered data with a high pass of 3,000 hertz, which would correspond to a 2-foot thick echo. And that smoothed the signal out. And if you look to the right, you see the spectrum that shows a strong low frequency resonance. That's actually the resonance around 400 to 500 hertz of the displacement transducer. That's the nature of its design. It's a piezo ceramic in a brass backing, a big brass backing that is our displacement transducer design. It's just pushed on the surface. Has a hard plastic tip that couples well. And you see a minor peak around 7,000 hertz. Well, that would normally have been the thickness echo, which is about 8.5 inches. The high pass filtering gets rid of, as you can see, frequencies below 3,000 hertz, between 0 and 5,000 here, are greatly attenuated. And you see a very clear echo. That small echo above is now much more visible and predicting 8.5 inches thick. That's the resonant echo front to back. So we also have platforms that can do more than one test. The NDE 360 is a touch screen with a compact flash. It'll do almost 10 tests or so of foundations, structures and pavements, impact echo and surface waves and pulse velocity. The Freedom Data PC does even more tests, including the seismic testing and cross-hole sonic logging and things like that. But it's much bigger. This is fairly easy for one person to carry around. This one you're often doing testing with 2 people because it is a bigger PC. This shows the SASW equipment, so you can see a better picture of it. This bar has displacement transducers. That's a similar design as what is in the impact echo testing equipment for point by point. You can spread those from as close as 6 centimeters apart up to 80 centimeters by adding this bar on the end. And you can use small to larger hammers. If you have a really large spacing that goes beyond 80 centimeters, which is about 2.6 feet, you can use accelerometers with a pair of accelerometers, magnetically coupled to some grease-mounted washers on the concrete, and see much deeper into it by spreading out a couple of them. So this shows testing across a concrete bridge pier with a wall crack to get the depth of the crack from the surface. What's not shown is the ball peen hammer, but it would have been hit on the left of this bar in line with those two transducers. So some example results from 2 different projects. The one on the right shows the crack tip depth. Here you've got a plot of velocity from 0 to 10,000 feet per second, and it goes from 0 to 2 feet in wavelength. The actual data is in this particular spacing around 1.3 feet. But you can see the velocity is relatively slow, around 2,000 feet per second. Then it starts to increase at about 0.45 feet in depth. That increase in velocity is associated with the fact that the perpendicular crack is not present anymore and the waves can travel faster. And we've had this confirmed by coring and other means on projects. So that wavelength is approximately depth of the crack is shown at the increase in velocity to the right. This was a little unusual, more like concrete bonded to a rock in a tunnel. It comes in with a normal concrete velocity. It then shows a drop in velocity at the concrete to rock interface, which indicates some bonding issue, and then a slower velocity associated with going back into the rock. You can actually model this in the most sophisticated way to get velocities of the layers and thicknesses of each material. So shifting gears a bit, one of the common problems in post-tension bridges and post-tension construction is certainly corrosion in the past of the tendon cables or wire strands that make up the post-tensioning. So certainly grouting has been greatly improved, and this is less of a concern than it used to be, but if things are not well grouted, this is down the Sunshine Skyway Bridge in Tampa, Florida. Those big piers were not well grouted. It was poorly grouted, and being the saltwater environment it is, the heat that it is, severe corrosion occurred. So we had an idea that we could use a scanner, better than point-by-point testing, which had been done on ducts to find voided versus grouted duct conditions. I came up with the idea. Dennis Sack, Dave Feidelman, our company, helped it become a reality and a US patent for a while. It's since run out. But it was a patented technology that allowed us to roll and impact as we went on a structural concrete surface. Relatively smooth concrete is not designed for rough concrete, but on a flat slab, on a structural wall, on the web wall of, say, post-tension segmental girders, you can scan this readily. So what you see there is the handheld nature of it. You can also put a handle on it and a weight for rolling on a slab. But what's shown on the underside are 2 impactors, a slightly larger one to see a bit deeper, and a small one that normally will be fine going up to, say, 18 to 24 inches. This one will go over 24 inches. That wheel is spring loaded, and there are sensors, piezo ceramics, every 1 inch around the perimeter of this wheel. There's the spring mechanism. So as you push it on there, it's timed so that when the sensor is in contact with the concrete, the impactor strikes the surface as a solenoid. This basic principle is similar to the handheld unit you saw earlier, but it's not rolling. So we were fortunate to be donated a girder that by a local company in Colorado when we had this research project for the NCHRP IDEA program. And we used 20 feet of the length of this long girder, we didn't need all of it, to grout defects into the 4-inch diameter ducts that are shown there in the girders. And the wall thickness was nominally 250 millimeters or 10 inches thick. So this just shows the styrofoam void that we placed inside, had a local repair contractor grout the ducts for us, and then tested them. So you can see them being inserted there. A fully grouted duct example showed an echo peak at 6,445 hertz, and that corresponded to an apparent thickness of 11.17 inches for the grout at a relatively young age of 3 days. So the grout was still, it gained its strength, but it was still soft. comparatively much slower velocity than the concrete. So it looked thicker than the normal 10-inch wall thickness. The empty duct, on the other hand, in the lower right impact echo result, shows a peak at 5274 hertz. That corresponds to almost 14 inches. This 22% apparent increase in thickness of the echo is due to the void. In a simple sense, void or honeycomb, void in a duct or honeycomb in concrete, causes it to resonate at a lower frequency because it is less stiff. There's a void or a honeycomb. So that shift in frequency is the fundamental indication of the presence of grouting issues in ducts. So this shows a cross-section view of the 20 feet we scanned, 240 inches, and the wall height from the top of the wall going down, in this case, 0 to 4.8 feet on that web. So we physically scanned from the top to the bottom, holding the scanner every 6 inches along this. So much more intensive scanning. On a normal project, we might scan 3, 5, or 10 feet apart to map out a girder. What you see for the top duct is a tapered void going from a 16% loss in depth versus the perimeter, and up to a more severe loss, and then 2 sections that have more severe loss. And you can see that the shift in the color scale on the right goes from nominally over 14 inches in the white down into the red and getting back to the more normal 11, where this was a fully grouted duct on the bottom. There were issues, even in our experiment, of getting the ends of this specimen grouted, even though we had a place for the grout to come out. So there are challenges, certainly, even in experiments. I kind of always joke that it's very difficult in research to build the perfect defect, and no offense to the contractors, that a contractor can do without even trying. So, but nonetheless, it's very true if you've ever tried to build the perfect defect in research. This shows a view that can kind of enhance the whole thing for you, where you see the normal concrete thickness around 10 inches in the blue. But jumping up, this is that top duct we just looked at. The thicker zones are readily apparent here. This type of 9 to 14 inch echo depth scale, 4.8 feet down the wall, 20 feet along the girder, shows very readily where the worst problems are in the severity in this type of skewed display. So this is a real world project in Colorado that they had concerns about the duct grouting in this new post-tension bridge, a long segment, but put in place with post-tension ducts and grouted. So they knew during the project they had some concerns about it. They wanted to check it. They first had us just demonstrate that the technology would work after the NCHRP ID grant. But we went and tested an ungrouted girder in the precast yard. The signature was it shifted from nominally 200 millimeters thick on the web wall, where this is 0 to 20 inches, scanning on the wall. In the ungrouted voided ducts areas, it jumped up to 250 millimeters, 10 inches thick. And you can see the signal at that point where the cursor is the time domain, frequency domain, and that's predicting 9.96 inch resonant echo thickness through the closely spaced 4 ducts in a row, looking like a 10-inch thick section instead of a nominally 7.5 to 8 inch that was typical of the results. So this shows that we could plot all of where the ducts are. You'd normally use, particularly if they're metal or have the tendons inside, you normally use radar to locate ducts. But again, we had enough data, we could easily plot where the locations of these voided ducts were. So now we went to the field. And oftentimes on bigger bridges, we would scan on the inside, up the inside of the walls. In this case, it was easier to get on the outside in a lift. Can't see the lift, but to scan up the outside wall. This might have actually been closer to one area where it was easy to get to. But pushing it with this impacting every inch in a line as we push the unit up the wall. So here's an example result in one area that shows a number of these ducts, even this zone, were well grouted, nominally 8 inches thick. But again, one duct showed a void at 10 inches. It jumped over to the right. That signal is shown here. Again, it's a 10-inch echo. This was confirmed by drilling and a borescope to be a void, and they did repairs. This shows another interesting result out of the project, because that's a curved girder and it's post-tension. There were debonded ducts, like a crack that occurred and produced echoes at 5 to 6 inches. You could still see a backside echo in this plot at this location, but this indicated that debonded ducts were due to curved girder stressing of the post-tensioning. So this is a research project done by Texas A&M University. It's NCHRP 1428, as you can see in the bottom. They built a large girder specimen and were concerned about using various NDT methods, NDE methods, to find grouted versus voided both internal tendon ducts and external tendon ducts. It's done by Dr. Stefan Hurlbau at Texas A&M. So they invited people to come in and demonstrate technology in addition to their own research. And so we participated in that. And this is one scan up the wall, about 7 meters from the east end, looking for an internal duct conditions. There's interferences at the girder floor because of access, but nominally the 300 millimeter, 12-inch wall thickness was fairly clear. There was shifts both places where we felt the ducts were grouted, but a greater shift occurred at the ungrouted duct location. Again, there's the signal, there's the peak from a grouted duct area. So this got reduced to a full-length plot from 0 to 23 meters long. You can see sketched in here the ducts themselves. This is the first, second, and third. And the 7-meter area where we were seeing some problems, and the second duct is right here. As it moves up into a thicker echo, normally it should be around 350 millimeters or less. You get into these colors, it's thicker, that is showing voiding. So the other interesting thing about the project was they chose to look at external tendon ducts. These have typically been sounded with impacts to hear hollow sounds, much like you do on a bridge deck, that are indicative of internal void. So these 4-inch ducts were grouted with voids again built in, just as the walls on the outside web walls had voids built in for the internal tendons. We adapted the scanner with wheels, a special configuration, front and back, to allow us to roll along that curved surface. It worked quite well in terms of impacting it and picking up the resonant responses of the duct. So this shows a plot for about a 4.5 meter length or so. This is the energy of the signal. There's high energy zones up here, nominally at 3¼ to 4 meters, and down from 0 to 0.8 meters, and then more low energy zones in the middle. This was indicated to be a void area. This as well, 2 void areas. That's the signal. It's a very high amplitude ringing low frequency signal. And it worked out well in terms of mapping it. So to summarize, for impact echo scanning of post-tension bridge ducts, we've tested over a dozen bridges. The grout defects in the ducts were confirmed with a borescope with good to very good agreement. We found voids that were filled with air and water. Bridges were tested with 1 to 2 rows of post-tensioning ducts. The fully grouted plastic ducts can be detected and verified as being grouted, even if the ducts are partially debonded. If it's fully debonded, we have trouble with that, of course. But normally, in most of our experience, both plastic and metal ducts have been reasonably bonded. The duct voids are grouted to fill the voids afterwards by the contractors to repair it, mitigate the risk of corrosion of the tendons. We've sold a number of our systems in use across China. They've built so many post-tension bridge ducts in their many, many projects as they develop their infrastructure. They do this as routine quality assurance for new construction. And the TTI research showed the impact echo results were fair to good for grout void detection in the internal ducts, and very good with 90% accuracy for the grout void detection in the directly able to be tested external post-tension ducts. So another technique you can use is ultrasonic pulse velocity. So this is a concrete column, a sign column on an interstate in Denver that was placed, and then they noticed some mortar on the surface. They decided to chip in and go after it, and unfortunately the concrete had not been consolidated. They had just dumped it. So 33-foot tall, 5 by 5 foot section holding up a large cantilever highway sign out over an interstate. So this was a great concern, as you can see and imagine. You lose 5% of your density in concrete. You've just lost 25 to 30% of your strength based on a Portland Cement Association study some time back. So consolidation is very critical. I'm also on the ACI 309 Consolidation Committee. So this just shows the test grid. We went north to south and east to west on a 1-foot grid. You can see the light colored grease spots. The one transducer is being held there on the north side, and 5 feet away on the south side, directly in line, was a receiving transducer. They were taking the data on the right into the PC. This shows a signal. At time 0, you hear a click in the sending source transducer. It's high frequency ultrasound around 50 kilohertz. And you see the arrival time to the receiver, time in voltage, this is time, at 372 microseconds or millionths of a second later. You do the math, that corresponds to a pulse velocity of 13,500 feet per second. Good, strong signal. This shows a very weak signal. You can barely see it. It's delayed. It arrives at 552 microseconds to the right at the cursor, and that gives a velocity of 9,100 feet per second. I want to point out that you can barely see that signal. It's the same scale, same amplification, and it's right next to the void in honeycomb. You can't test on the void, but it is right next to it. So we could have given the project report with 330 values the speed of sound, but that's not so easy to look at. So we then did tomography. And tomography is much like a CAT scan, except instead of being the amplitude of an X-ray, in medicine, this is the speed of sound tomography. So you can do straight ray testing, variety of locations. The more angles and more crossing ray paths you have, the better image you'll get. You can allow in the analyses for bending or curved rays. So the waves, in a simple sense, can pick their own fastest path to go from the source to the receiver. You're solving for the velocity of all of these. You can think of them as pixels in this 2D cross-section of, say, a column. So what we did is test every 1 foot vertically, 32 slices, top to bottom. And we tested north to south and east to west on a 1 foot grid. And of course, that's a relatively large pixel, but by analyzing the data, even with this limited data set, we were able to see good velocities above 12,000 feet per second in green, moving into the void pore in this area. Technically, it was interesting that of the 32 slices, 16 were all green and good. The concrete self-consolidated by dropping it from that height. But unfortunately, and it was randomly distributed, 16 slices had a lot of void and poor quality concrete conditions, and they had to tear out the column. There was no repair to it. So this is another project where there was very dense reinforcement in these large piers of this post-tension segmental bridge over a river. And at the piers, there was so much steel that even with a good mix design and everything else, they saw some surface honeycomb issues that caused them to want to check it. So we did ultrasonic pulse velocity with tomography analyses. Here, the axis, because they're massive piers, was really around the corner. So we had a grid where we would test on this front face and then around this side. So we had semi-direct angled testing with crossing ray paths, as shown here for semi-direct around the corner. So you can, in software, you can slice the data. Again, it was done in horizontal planes, but the slow velocities are down into the blue colors, and the good velocities, as you can see in these color scales, of thousands of feet per second, basically 11, 12,000 feet per second and higher. So this was showing where the honeycomb void was in these different cross sections. Here's one where there was no void, it was solid. So this allowed the contractor to guide the epoxy injection repairs by drilling into these areas to fill these small honeycomb and void areas with a good epoxy. So the advantage is primarily, it does take a picture. It's worth 1,000 words. It can image internal void, cracking, and honeycomb. We use this on dams, we use it on drilled shaft foundations, a variety of things that we do ultrasonic, sonic tomography on. You can image in a 2D sense, and if you do even more angle testing, you can get a 3D fashion image that's true 3D and not 2D slices. It does take some training and experience for the analysis, but the field data is fairly straightforward. It does take more testing, of course. So slab impulse response is a method that was first developed. There's an ASTM standard for it listed there. There's an ASTM standard for the impact echo and pulse velocity that were listed as well. But here you hit with an instrumented hammer, you impact the concrete slab or pavement, looking for a void below it with a geophone on a flat slab. It's much more flexible, less stiff, much more mobile, a lot more vibration amplitude per unit force when it's underlain by void versus good subgrade support. If you're testing an angled a wall, say, or a tunnel where the slopes are more than 10%, you can use a Wilcoxon velocity transducer and test at any angle. You're measuring mobility, velocity divided by force versus frequency, and flexibility. And the inverse of that is stiffness. So high mobilities and flexibilities, correspond to flawed structural concrete even. It's been extended to be used for finding problems in structural concrete up to 2 feet per the ASTM standard, such as void and honeycomb. It's more comparative, more of a overall structural stiffness test, if you want to think of it that way, but it still can find flaws. It's just not necessarily going to tell you the depth of them, like impact echo and surface waves can give you more insights into that. So this shows example time domain that was taken from a steel line concrete pipe conduit on a dam. The impulse hammer force is shown about 4,000 pounds force on the right. The sound response is a tighter signal. Keep in mind this is steel. If it was straight concrete, it'd damp out even quicker. But this is time and voltage in the response in inches per second for each of these units. So as you look at this, there's a void hollow response. It's lower frequency, more irregular. This is going to show a less stiff condition. So for structural applications, we did a lot of testing on these pre-stressed box girders for void and integrity. And this just shows the geophone could be used in an upside down fashion and impacting with the 3-pound instrument hammer that measures that impact force. So the mobility plot here versus frequency, and what you see when the coherence is near 1, this is good quality data. This is relatively low, relatively smooth. Impact echo testing showed it had a normal thickness of 6.7 inches for the bottom slab of this pre-stressed concrete box girder on a freight rail bridge. By comparison, where impact echo showed a 2.6 inch normal thickness, it was a much higher mobility, much lower flexibility, not well damped. This is showing the fact that it's a thin section. So it was confirmed in both cases to be that. So shifting gears again, the ultrasonic thickness testing can be done to check for loss of steel section indicating corrosion. What this shows is if you have a full section, like in this plate steel that was tested, you'd see the full thickness echo. If you have internal corrosion, like on a pipe or something, or the inside of a vessel, you will see corrosion on the inside that results in a thinner echo. And that is simply indicating the loss of thickness due to corrosion. A typical 5 megahertz probe coupled with ultrasonic gel to the steel. So we often do this kind of testing with an ultrasonic pulse echo flaw detection type gauge because we're looking for problems, and that's what's shown here. You can get more economical ultrasonic thickness gauges. But this old bridge, built in the 1950s on an interstate, showed loss of section up to 60% in the girders, and the section losses were located both in the web and the flange. This is near the cross beam where the joints were not performing well and all the de-icing salts were coming down onto the girders. They'd run down the length of these girders and pond in the middle. So there were loss of sections throughout the bridge. So this example is taking advantage of the flaw detection. You can't really do this well with a thickness gauge. You get a result, but you want to see the data when you're looking for flaws. So comparatively testing and knowing the anchor bolt lengths that were supposed to be there, this is a broken anchor bolt. It's showing on the screen of the unit a 6.035 inch echo that is a short bolt. Should have been 2-foot bolts in this case. So this is a good thing to check on anything where you might have broken anchor bolts. The unit we use can go out to 32 feet for some very long embedded bolts. Most units won't go quite that far. But this shows we're shifting gears to the second part of the talk today. And I think I need to speed up a little. So bridge deck condition assessment methods, impact echo scanning, surface waves for mapping on asphalt overlay decks, ground penetrating radar. We're not going to discuss infrared, but can also be used for top steel delamination, and the Galvapulse, and you do some destructive coring. So this just shows point-by-point testing, seeing a sound echo in a deck. Oops. Seeing tight cracks where you still see a thickness echo plus a higher frequency echo from the crack. A bottom delamination where you see a deeper echo from the bottom steel. And a top delamination where if you get under 3 inches, you usually don't see the echo specifically. You will see a flexural response. That's that hollow drumming sound you hear in chain dragging. So we wanted to get it much more rapidly done. Point-by-point testing, impact echo is very accurate, but point-by-point testing takes forever on a deck. So we developed a sonic surface scanner with rolling impact echo and rolling surface waves with some NCHRP IDEA funding. Here I am pushing a unit on a deck in Delaware recently. I do go to the field occasionally, but nonetheless, we're rolling it. There's the rolling wheels, the impact echo brass transducers. Here's a unit showing the displacement transducers and the solenoid impactors. They're offset to hit left and right, typically spaced a foot apart as you roll it slowly, walking a mile and a half an hour. This is a close-up of those sensor wheels. It does couple well to the rough concrete. It hits it fairly sharply, so we can lose some data, but we're getting tests every 6 inches as we're rolling, so it's a lot of data. You can space them from 6 inches apart on the wheels to 9 to 12 to 24 is typical, and 1 foot is a common spacing for mapping delaminations on decks. You can line them up for doing surface wave testing. Then you get an impact echo test on the left and surface waves between the wheels. That's used for asphalt overlay decks. So this project with 2 bridges, 600 by 36 feet long, brand new bridges. They scanned with 42,000 tests in 1 day for a test every half square foot with a 1 foot spacing between the wheels. It was done because they were quite concerned. It's in the desert Southwest near Las Vegas, but the concrete was a couple hours out of town. It set up and had a lot of drying cracks, surface drying plastic shrinkage cracks that were of concern that maybe the concrete wasn't well consolidated. So we tested at a 1 foot spacing in grid lines on these 2 bridges. It is also well coupled, the deck was, to the underlying diaphragms and girders at the piers. So as we rolled along, we were using a wagon at that time. We just rolled it along, pulled the wheels. Here's a close-up of how rough that deck was, because it set up too fast. They couldn't finish it very well. So you can see it was a very rough deck, hitting left and right with impact echo on the 2 wheels. So here is a 100-foot scan line showing the 300 millimeter thick, 1 foot thick approach slab, the 8 inch thick deck. We were looking for an increase in thickness that was substantial to show internal void and honeycomb. We didn't find it, which was fortunate. You can see here the time domain signal is very clear and strong on that rough deck, and a very good peak right about 8 inch echo of this cursor location. So that represents 200 tests. This shows the overall results, and the thicker approach slabs in the color scale of about 1 foot are shown at each end. A lot of it was the green normal thickness. You can see where the diaphragms at the piers are present. You can see the girders, which are also looking thicker. But we did not find anything indicative of honeycomb internal void, so they had to seal the deck and they moved on. This is a research project that Rutgers University did on the Sharp 2 non-destructive testing of bridge decks that they invited people to demonstrate technology in Haymarket, Virginia, near Washington, D.C. Their deck area was limited, but it was very corroded. It was a good test site. And this shows the results that we got from impact echo scannings with the sonic surface scanner. So the thickness scale is ranging from basically the normal thickness to some, right in here is the normal thickness, to the bottom delaminations at a shallow depth in light blue. So if there's not a top delamination present, you can check the bottom. To the incipient delaminations, which are showing some delamination tendencies, but not as severe as the more open full delamination type cracking in red. So the yellow and red are mapping the near surface delaminations, and the light blue is mapping the bottom. So you can get the areas of delaminations. Top was 14%, incipient was another 13%, so about a quarter of the deck had issues, and only 5.7% at the bottom, but there were issues down there as well. They took the deck section, Turner Fairbank's laboratory, and they kept it there after they demolished the bridge as a future research full-scale model. So we also did GPR deck scanning with a system 2 gigahertz bipolar antenna, which has front and back antennas and left and right antennas. So we compared that on this project with the impact echo results. By going 2 directions with antennas, you can see more things, as is quickly shown in this slide, where the horizontal left to right channels found the top steel, but not showing up in the front to back for the scan direction. But the other pair of antennas from left to right, the VV channels, found the deeper post-tension ducts that were inside this member. So it's useful to be able to do that in one scan and see both results. Comparison of the methods for impact echo on the top over this short section of 85 feet, 1 lane width, with GPR in the center, which was calibrated based on correcting for depth of cover. Attenuation of the signal is how you indicate corrosion and potential for damage corrosion. Agreed pretty well. It was calibrated based on the impact echo results. And on the bottom, the Rutgers researchers had done chain dragging, acoustic sounding, listening for the hollow drummy sound to map the top surface delaminations. So all these, 3 of these plots were focused on only showing the top delaminations. Interestingly enough, cores were taken because it was noticed that we predicted a problem over here with the sonic surface scanner and impact echo that the sounding did not hear. So when they cored this location, there was a delamination 3.5 inches deep. The acoustic sounding did hear the chain dragging, the delamination at 2.5 inches deep shown at core 5. So we've kind of concluded it's hard to hear much deeper than 3 inches in concrete by ear in sounding. So we went on to just go very fast here. We were involved in another sharp study on hot mix asphaltic concrete delamination of asphalt pavement lifts that was done by the National Center for Asphalt Technology at Auburn University in Alabama. We went on to test highway pavements in Florida, Kansas, Kentucky, Texas, and New Mexico, all about finding debonding between the lifts. So we built a very simple prototype frame so we could go straight only, but we set it up with the sensors lined up to do an impact echo and surface wave test 6 inches apart, here and here, another set of wheels 6 inches apart, and another set here. So we could test half the lane and make it a little faster. So what we found in that study, here's a good result. The surface wave, it was relatively cool, so the asphalt was similar in velocity to the concrete. And you can see from wavelengths of 0.2 foot to 0.9, good velocities, 5,000, 5,500 feet per second. So that was a good, no debonding was built into this pavement. We did all this testing initially blind. Later they told us what was there and we learned from that, but we were able to identify with surface waves a drop in velocity of the asphalt at the depth of a thin paper delamination that was a debond, a simulated debond. They also used dust for debonding in the full study. And that drop in velocity of about 1,000 feet per second is because of the lack of contact at the debonding, like a delamination in a deck. So from this, we were able to map out very well debonding of new asphalts when the tack coat doesn't take between lifts of an asphalt pavement. That led us to demonstrate the technology for the Colorado DOT on an asphalt overlaid concrete deck. There's a lot of different things you can do for this. Sounding, it's hard to hear. Infrared thermography is only seeing the surface 2 to 3 inches, plus you have debonding issues at the asphalt concrete interface. Impact echo scanning can be problematic, particularly as the asphalt gets hotter, above say 80 degrees, and it's not going to resonate so well. Radar can be complicated by de-icing salts and moisture. It's often present at the asphalt concrete interface. But surface waves detected delaminations. So we applied it. Here we're pulling the wagon and the wheels. You can see they're lined up on the sensors on a real deck that was being, 2 of them actually, that were being repaired, renovated on the east side of Denver by the Colorado DOT. So we tested from the asphalt. We knew nothing about what was underneath us. The results showed us, and these are the signals you haven't seen for surface waves. The big spike is the surface wave in time. When you window in on that, you get phase, which is showing velocity versus wavelengths from this phase analysis of the data. Well, this was good velocity. This is bonded asphalt and sound concrete, around 5,200 feet per second. This shows a result with debonded asphalt at a wavelength that corresponds to 3.5 inches. The velocity dropped about 1,000 feet per second. This delay in phase is this drop in velocity. So this was an area that had debonded asphalt. This shows at a deeper depth of 5.1 inches, a greater wavelength, a drop in velocity that would correspond to the depth of the top steel. That's a delamination. This glitch here, this delay, is causing this drop in velocity. This shows 2 drops, the asphalt debonding at 3.2 inches, and then at the depth of the bottom steel around 7.4 inches, another velocity drop. So this is the debonded asphalt area in the phase and the bottom concrete delamination. So the check we got, we gave them this report and everything and reported our results, with delaminations being the worst in the red to the yellow for this section from 50 to 70 feet. They scraped off the asphalt. They used hydrodemolition to blast away the loose concrete, and you can see the good correlation of where we predicted delaminations by testing through the asphalt here. You can see that the concrete has been removed because it was cracked up, delaminated because of the corrosion expansion of the steel in these areas. So there's good correlation. We've gone on to test over 30 decks with asphalt overlays for Colorado DOT and others. using a combination of impact echo and surface waves combined with radar. So the scanning for detection of debonding, this is a 4-inch white topping overlay. And here we are pushing the scanner along. 1-foot grid. We found areas of debonding conditions between the white topping and red. Shallow delaminations, low frequency flexural responses showed up even shallower than the 4-inch thickness of the white topping, as well as sound concrete and some partial debonding in these colors. So this was mapped out on this deck. It had very good resolution. Impact echo scanning is very accurate for project level projects where you have traffic control anyhow. It's better than GPR and chain dragging. Found bottom delaminations where there was not a top one present. Profiled the deck thickness. And surface waves used for mapping out delaminations, the asphalt overlaid concrete bridge decks, and impact echo scanning mapped out the debonded white top concrete deck. So I'll close very quickly with some comments about galvapulse. This is another technique where you tie to the steel, you use the unit, you have water coupling, and you can do 3 measurements. But you can estimate roughly the corrosion rate by projecting a current with a galvanostatic pulse. And you get 3 results. The half cell potential, which when it's more negative, as this table shows, it's very likely corrosion is actively occurring right at the joint. Very negative half cell potentials of this Indiana bridge deck. Very low concrete resistance. All the de-icing salts went towards the joints, lowered the concrete resistance. And the corrosion rate was highest at the concrete resistance. So cores and laboratory tests, I think most people are familiar with. Chloride testings, we do rapid chloride testing ourselves to estimate the remaining surface life as the concrete acidity increases when the asphalt gets closer to the steel and starts corroding. Phenolphthalein for carbonation depth done in the field on the cores estimates the remaining surface life due to carbon dioxide, which penetrates. The acidity again goes up and causes corrosion when it gets to the depth of the steel. Compressive strength, unit weights, pulse velocity can all be done for correlations and checking the strengths. Petrography can be done by others for specialized laboratories to look at cracking, hydration, air void spacing, etc. The last thing I'm going to comment on are you can correlate, of course, with cores and doing ultrasonic pulse velocity of strength. The ACI document from '89 talks about the velocity of fourth power is proportional to concrete strength, but you have to correlate if you're going to use this seriously with cores and pulse velocity testing to estimate the strength per ACI's 228.1R document. So this shows plots from rapid chloride testing on a deck, various locations. When you get above about 0.2% by cement, you are getting at a threshold where if your steel was at this depth in this range, you would see corrosion of the steel because it would become acidic. So sharp research, as I just mentioned, when it gets above 1.2 pounds of chloride ions per cubic yard, or 0.2% by weight of cement, 0.03% by weight of concrete, at the depth of steel, the rebar will start to rust. So different conditions have different thresholds. It can vary, of course. You always should check the steel for actual corrosion. But it usually comes from de-icing salts or if you're close to the ocean, sea salts. Fick's second law of diffusion for remaining surface life is commonly used. With this equation, knowing the age of your structure, the chloride levels, you can determine the diffusion coefficient for the, say, 40-year-old bridge. Then you fit that data, the best fit line. You can use the least squares approach from your data, usually interpolate the surface because that often gets washed out by summer rains. And this just shows an example of a recent project we did where applying Fick's law, the rebar was at 68 millimeters, about 2.8 inches from GPR to find depth of cover, that the 0.03% threshold by weight of concrete coincided with plotting out a 200-year remaining surface life curve to predict that that deck was going to last 200 years. The chlorides aren't that high. This is in North Texas as opposed to being in, say, Michigan. So the other thing that can cause corrosion is carbonation penetration from carbon dioxide. Taking cores in the field, wash them off, spray them with a phenolphthalein testing solution. And this one was clear from the surface after spraying it to about 7/8 of an inch, which indicates the carbonation went up to 7/8 of an inch deep. It's proportional, the depth of cover, you can know that from radar. In the time, you know the age of the bridge generally, so you can solve for the carbonation coefficient. Then you can apply that in knowing the depth of your steel carbonation coefficient, how much life you have remaining, which is normally much longer than due to chlorides in the bridge from a carbonation perspective. So I started Olson Engineering in 1985 and Olson Instruments in 1993. We're happy to work with you either as a consultant. We often are working with other engineers in that regard and contractors. And if you're interested in instrumentation, we started making instruments in 1993. I want to thank you very much for listening today. I will allow time for questions, of course. We can stay as long as you can stay. I did manage to finish it about 57 minutes. Thank you very much. So are there any questions for the chat? And I'd be happy to answer them.
Is there a method to predict the shallow depth and exact location of delamination on a deck tested through impact echo?
You can do that test, not with the scanner, because there you will have a hard time seeing echo frequencies much below to correspond to, say, 3 inches, nominally 24,000 hertz. But we have made a special device. It's an option on one of our point-by-point units where you impact a smaller solenoid on a steel anvil, small steel-like bearing, almost like a BB. And that high-frequency impact will get you shallower echo depths, say down to 1.5 inches. But at some point, it will just respond as a really low-frequency flexural response of the loose piece of concrete.
What is the standard that you use to determine the remaining service life of concrete and cores?
Okay, that standard is part of what that one plot showed, where for that particular bridge deck and the determined diffusion coefficient from the chloride testing, that it came in at a 200-year remaining service life. Other bridges we've seen less than 10 years that are in areas with a lot more use of de-icing salts. So the standard, if you approach it from a new materials perspective, and Life 365 and other programs can estimate new materials and how long with laboratory testing you can predict the service life to be. Most bridges, as you probably know, are being designed for 75-year life. That used to be a 50-year design life. And of course, some people are pushing for a 100-year service life. There are also treatments by vector corrosion technologies and others where you can do electrochemical extraction of both chlorides and carbonation effects, where you bring alkali back into it, but it's costs, but you can remove the chlorides and put alkalinity back into it to mitigate the effects of carbonation, which can be warranted if the deck is worth saving and you haven't lost much of your steel.
What is the best equipment for rebar locating and measuring bar size and thick walls?
Well, we use a variety of equipment. And certainly you can look at the ACI Concrete International magazine. We prefer ground penetrating radar. There's some nice smaller scanning units out there that can be used and both locate the rebar. As far as determining the size, you have to have like one bar on top of another, and you might get from the radar plus or minus one bar size at the top of the bar. But there are a number of cover meters by Hilti, by Prosec, by others. Certainly some of the major radar manufacturers are GSSI, of course, Sensors and Software. There's a range of folks, IDS GeoRadar, Impulse Radar, that make the radar equipment. And German, James, other groups have them. Your best bet is looking Concrete International magazine. And if we get to have a convention, go to the ACI convention in the fall in Raleigh, North Carolina. A lot of equipment will be there.
What is the wavelength of the galvanostatic pulse, and where are the electrodes for applying the pulse?
Okay, the situation there is that you water couple it, and it has an external ring to try and guide the pulse, but you're actually polarizing the steel for about 5 to 10 seconds is typical, and you watch the decay of the polarization. So it's not really a wavelength, but this polarization decay is related to the so-called Stern-Geary and Toffel constants that allow you to estimate the corrosion rate from that decay. And it is nice in that if it's not actively corroding, by projecting that current, you can see that it get a corrosion rate still. You never do the corrosion testing when it's near freezing because the corrosion activity is not occurring.
UPV is a function of concrete E and density. How applicable is the Leslie and Chessman criteria to SCCs, which typically have lower E values than conventional concretes?
Okay, so the question has to do with ultrasonic pulse velocity being a function of density and modulus in Poisson's ratio. And the question is related to self-consolidating concrete, and they want to know specifically what again?
How applicable are the Leslie and Chessman criteria to SCCs, which typically have lower E values than conventional concrete?
Oh, it's still generally applicable, but you might find from, say, testing cylinders on your project prior to crushing them that you would get a lower strength correlation, lower velocity with the strength. So the answer is it always varies. Unlike steel, which has constant velocity, of course, concrete has a wide range of velocities depending on the mix design and the age of curing. Increases substantially in the first days of curing. And after 28 days, the increase in velocity is not as large.
Okay. What do you prefer for detecting water leaks in basements with high GWT? I think the question is, what is GWT, right?
Yes. So if you want to detect a water leak in a basement, obviously there's two approaches. Well, I shouldn't say obviously. There are two approaches that we have used. One is ground penetrating radar, because you will see wet wall areas versus dry wall. And if it's a concrete block wall, you'll also see whether it's grouted and whether steel rebar is present vertically in, say, in the spacing between the cells that it should be there for. And that also has a sensitivity to dry and wet walls. The capacitance moisture test is a relatively low-cost device that you can again find in catalogs that will show you wet walls by measuring the moisture content approximately. So by scanning with that, but you're only sensitive to the first quarter inch of the wall.
How fast can you do non-destructive testing? What is the fastest method for heavy traffic bridges?
Okay, it's something that we can do. We haven't pushed it hard, but we are moving more and more to looking at, a lot of people do it, infrared thermography combined with ground penetrating radar combined with good cameras can go 40 to 60 miles an hour for surveying both decks and pavements. You saw today a largely project level approach, which is far more accurate because it's a detailed mapping. In impact echo, simply there has not been a good way yet to do impact echo fast.
What are the advantages of using sonic waves versus magnetic flux to detect corrosion of PT tendons and rebar?
Well, the magnetic flux leakage work I've seen mostly, and it's been done by Adirad Aziz and Namimi and others. He's down at Florida International University, the chairman of the Civil Engineering Department, is used to find the internal corrosion, say, of tendons, and to see the change in the magnetic flux. So in that sense, you are now directly testing the metal. That's the attempt. And there are scanning units, also BAM, which is a German research laboratory in Berlin. BAM has done a number of work in this area. The impact echo is primarily going to work for finding the absence of grout and not telling you the corrosion or the condition of tendons. Certainly, if you have access, if you can evacuate people and you have access to both sides, you can do detailed X-ray radiography of tendons and image wire breaks if they've separated. But that's a tomographic approach that can also be used, but it has the limit of keeping people away from it because of the high radioactivity associated with the radiography.
How about IR using drones? Is this proven technology yet?
I'm going to let Ryan answer this question because he's done work with drones, all kinds, in his role as a geophysicist at the U.S. Army Corps of Engineers until he joined us in Vicksburg, Mississippi, the Engineering Research and Development Center. And so he has pretty good drone experience. So go ahead, Ryan.
You can use IR cameras on drones pretty easily. The question is, what is your target? What are you interested in? A lot of this ends up being a legal logistical issue due to flying over active roads at elevations low enough or altitudes low enough to actually get the resolution you need without interfering with traffic, which the Federal Aviation Administration generally frowns upon. But if you have additional questions related to this topic, you can just send us an email and we can follow up with you.
Next question. What is the best method to identify or locate the voids that are hidden below the rebar?
Okay, it depends on the size of the void that you're looking for. The ground penetrating radar will normally not work well because there's too much steel. If you had plain concrete, you could probably see the voids okay. The radar also is not good at finding tight, thin cracks. You know, you need to have some air gap there or water fill gap for the radar to show up better. So I don't think the answer is radar. I think the impact echo does a reasonable job if it has a reasonable size of void. You can also use another technology called ultrasonic pulse echo for concrete. And both the Mira system by Garmin Instruments is out there, and the ProSec has a similar ultrasonic pulse echo system that takes advantage of shear or compressional waves. You get a test area as you push these many kind of like finger sensors, but they're piezo sensors against the concrete. And then you will get a true reflection image coming back out of it.
It looks like you have found a way to find delaminations under waterproofed and HNA decks. How accurate are the validations that you have done?
Validations have been pretty accurate because there is usually going to be some repairs. There's some coring done to check things as well. So I wouldn't say it's perfect, but it's been very accurate. And it's been shown in the Rutgers study and others that it was the most accurate for mapping out the delaminations. So the surface waves was the innovation that lets us look through these barriers. Now, if it becomes a true, almost air gap situation, none of the stress wave methods will cross that, because then it is the end of that in terms of being really open.
The next question just says groundwater table, which I don't think is necessarily relevant to this discussion.
No,
so why don't you send us an email?
No, the groundwater table, he was explaining that he wanted to find the water on the outside of the wall.
Okay.
So you could, again, I think with lower frequency radar, if there wasn't too much steel, you might see the water table change with a vertical scan up the wall. But you're typically looking for just a moist wall on the inside and the capacitance moisture for that combined with the radar.
What NDT method is best to assess the quality of concrete with close distance surface cracks?
Okay, if you're talking about perhaps freeze-thaw cracking damage or alkali silica reaction damage that's not so severe, you can comparatively test where it's not cracked to see the velocity versus wavelength versus where it is cracked with surface waves. And I would use the bar, the SASW bar. You can get short high-frequency impacts and get down to 1/10 of a foot, and that's a very short wavelength. Of course, you can always take a core and confirm it with the microscope. It's very good at really fine micro cracking to find that as well. If the cracks are super tight and not much loss of contact, then the surface waves won't be as sensitive.
What is the best method to assess the durability and service life of concrete structures affected by corrosion?
I think it's an integration. Chris Barnes, who was formerly at Dalhousie University, is a Canadian and has worked with our company and has some of our equipment. Okay. He looked at the concept of using ground penetrating radar combined with laboratory testing, sophisticated testing to get the diffusion coefficient of chloride penetration. And then on new bridges, he was proposing that you would reward a contractor based on how close they came to meeting your specifications to get a longer service life. But you can do the same thing on an existing bridge, but you'd have to take some cores. You'd have to do ground penetrating radar. If you want a damage map, I'd suggest the impact echo scanning approach.
What sensor is used for impact echo receiver?
That's a displacement transducer, one we designed. It's a piezo ceramic that has a hard plastic tip over the sensor to protect it. You can break them, but they're pretty tough. And it does not require generally coupling, just pressure to make sure you're on concrete. It's a small enough unit by hand that you can push the handheld unit and find a place where you'll get a good impact and a good coupling of the displacement transducer tip. It's kind of conical in shape.
For coring, do you suggest going all the way through the structured deck?
Well, we've done that both ways, and there's pros and cons. I would generally say not to, but if you need to core the bottom steel and you have to take a risk, you'll cut through that. I was on a project in a building, we're in Terracotta, an old building in Washington, D.C., where the coring subcontractor went all the way through unexpectedly and dropped a core on somebody's desk. If you're over an interstate, you'd better have a way to catch the core and not be in traffic if you're going to core all the way through.
Can IR or visual methods from a drone be a standalone inspection tool to reliably identify delaminations?
No, it's all visual. What we do is look beyond skin deep. Visual is very important. I'm an NVS certified inspector for bridges, for safety of inspections of in-service bridges, as a number of our people are. But we do these detailed studies and assessments of structures combined with, on bridges, with the NVS ratings. So to be visual alone, you can only see the surface. And to map out the laminations is not so good. Now, obviously, if it's spalled, you can see that. You can use infrared thermography. There's a variety of approaches there that can see the shallow delaminations within 2 to at most 3 inches. Can also be done. And that's a simple thing to walk and see that. So if you expand visuals, include thermal imaging with infrared thermography combined with a video or a still picture, then you can sort of do it visually better. But again, you're going to see skin deep, maybe down 2 to 3 inches at most.
What about replacing the geophone in the impulse response method with an accelerometer, a piezo type rated for low frequency or a MEMS, and then integrating the signal?
You can certainly do that as long as you get the frequency response you want. You normally want to get down to, say, 20 hertz. The Wilcoxon velocity transducer I mentioned that we sell as an option in our system is an accelerometer that's electrically integrated to be a velocity output. And that's probably a better approach to take. But what you're proposing could work fine as long as you compared it with, say, a 4.5 hertz geophone to see you got a good response.
Is there any study on the correlation between chloride content, UPV, and half-cell potentiometer readings to assess and ascertain the corrosion of concrete?
Well, there's a number of studies on all those things individually, generally not including ultrasonic pulse velocity.
Is there a correlation between half-cell potential, corrosion rate, and electrical resistance?
Yes, you will see that in the half-cell potential, it is more negative when it's actively corroding. You will see that the resistance is lower. And there's also resistivity. The ProSec and others make resistivity measurements, which are different than the total concrete resistance measured by that galvanostatic pulse unit I showed you, which is now called the CoroMap by Force Technologies out of Denmark. But so resistivity mapping is certainly good also, because you will see lower resistivity and that correlates with a greater likelihood of corrosion, much like the half-cell potential.
Are these methods and tools uniform across all NDE consultants? In other words, what is the best way to request or write a good RFQ?
Well, certainly guidance is given somewhat technically in terms of the ACI documents and the ICRI documents. So you can use that as a resource. There are example specs. I'd also point you potentially, for bridges in particular, to the Turner Fairbanks has an NDE laboratory headed by Dr. Hoda Azari. They have a good website that can also give you some guidance. And they will have some specs. Years ago, we wrote a spec, for example, for cross-hull sonic logging that became modified and adapted by many DOTs. But it starts with referring to a standard if a standard exists. Surface waves doesn't yet have a standard. It is in the ACI 228.2R document, for example. But the other methods at least have a basic standard.
That is it.
Oh, I want to thank everybody for hanging in there and listening to this talk. We'll give another one. We will send you, all of you to register, a link to where you can see it again if you'd like to, or share it with some colleagues. And look forward to hopefully being of service in one way or another to you. And as we've all been saying, let's stay healthy and get back to work. We are getting to work, but kind of slow in terms of people wanting us to show up. Not surprisingly, right? Now things are looking more positive that way. On a happy note, let's hope for the best this summer. And thanks again for attending this seminar.